Okay, it's pretty quick, it's pretty easy, pretty fast when you have the data in front of you, all right? Now, follow-up questions, you might get these. Could any of these integral approximations represent approximations for the area of the region? Well, here's how we answer that. Area has to be a positive thing. You can't have negative area. So in order to have a positive area, you need all of your y values to be positive, okay? Are all of the y values positive? The ones we see in the chart are, but are the ones that we don't see also positive? Well, that's where this comes in. It actually tells us that right there, that f of x is greater than 0 for all x. So yes, because area has to be positive, we could say yes, or we'll just say yes because, I'm not going to write it out, but yes, this would be part B. Yes, because f of x is greater than or equal to 0 for all x. Okay, that's all you have to say. If that f of x greater than 0 were not there, then we can't say for sure that it is. Again, because just because the y values you see are positive doesn't mean the ones in between there aren't. Area has to be positive. Can't have negative area. And then a review question, part C, approximate the derivative at 1. So f prime of 1, squiggles. Remember that to approximate a tangent line from data, we have to use the secant line. And in this case, we come up here and we realize that 1 is in the chart. It's in the table. So now that they're equally spaced on either side, remember College Board will allow you to use the values to the left, like 0.5 and 1, or the values to the right, 1 and 1.5, or the 2 on either side. I'm just going to go ahead and use these values here. Why the heck not? Now, be careful. We have to show the difference quotient. In the difference quotient, it's change in y over change in x. In the table, we have x's in the top and y's in the bottom. So we have to be deliberate and write the bottom first. And then get in the habit of doing right minus left. So I'm going to put 7 minus 6 all over 1.5 minus 1. That'll work. Full credit. That's your 2 for 1 again. The difference quotient, and it's numeric. Okay, right minus left on the y's, 7 minus 6, over right minus left on the x's. Okay. All right, so that's like a sample free response question there. Questions on that one? All right, 11. Let's look at 11. It's another table of values. If f is continuous, so again we have continuous function, approximate the integral from 1 to 8 using the numeric integrals. All right, so again the first step is to look at the interval. We're going from 1 to 8. Are we going to be using all the data points then? No, we're not using the 0 and we're not using the 10. So it would be easy to like overlook that and get carried away and just use all of them. That's not what we're going to do. The next thing we do is we calculate delta x. From 1 to 3, that's 2 units. So is it 2 all the way across? Not necessarily. From 3 to 6, look at that. From 3 to 6 is 3. Oh, okay. So now we have different delta x's. From 6 to 6.6 is 0.6. And from 6.6 to 8 is 1.4. So every width is different. Now, when your delta x is different, you can't factor it out. Okay? So you're just going to have to go back to thinking of it as like individual pieces. All right? It's not a big deal. Now, how many delta x's did we calculate? 1, 2, 3, 4. So in this case, n is equal to 4. All right? Let's give our integral a name. I think I'll call it w this time instead of I. Just pick a variable. And here we go, part A. W, the integral, is now approximated by, let's do L again. L sub 1, 2, 3, 4. We got 4 subintervals, so L sub 4, which equals, all right? Now here we go. It's going to be the width 2 times which 3 are we going to use for left endpoints for the height? The 3 on the left or the 3 on the right?
Left.
Left, yeah. So it's 2 times 3. I like to put parentheses around them when I'm multiplying. You really only need one set of parentheses, okay? But don't just put a dot there. Plus, the next width is 3 times the y value to the left, which is the other 3, plus the next width of 0.6. And it could be helpful to draw these lines to the left, times 1, plus the width 1.4 times the y value to the left, which is 5. And again, it's still left justified. We're not using the y value of 8, which is on the right end. So I did width times height plus width times height plus width times height instead of height times width, whatever you're comfortable with. All right, for the right endpoint, we'll say W can be, let me use a different color here. The integral W can be approximated by R sub 4. And here's what it's going to look like. The width 2, but now we're going to use the 3 on the right. 3 plus the next width of 3 times the 1 plus the 0.6 times the 5 plus the 1.4 width times the 8. So notice drawing the arrows from the middle where we put the width to the right, it's kind of helpful because now we can see we skipped the first value of 3 and we use the rightmost 4. Okay. Of course, the average of those two is the trapezoidal. Let's think about the midpoint here. Can we do a midpoint here? If I skipped every other one, like if I went from 1 to 6? No, because the midpoint between 1 and 6 is 3.5. It's just the average of those two numbers. We don't have the x value at 3.5. We have 3, so we can do some kind of intermediate thing, but not a true midpoint. So you're not going to be asked to do the midpoint, okay? So let's just go to the trapezoidal. Let's choose red here. I'll choose red. So the integral can be approximated by t sub 4, which is, now, if you want to do like 4 individual trapezoids, that's still fine. But I think it's still worth factoring out the 1/2 because that is common in every term because it's part of the formula. Let's come over here and review. The formula for a trapezoid is 1/2 the sum of the bases times the height, which for us is delta x. So we're going to still have this component going all the way through with the 1/2 factored out. So here we go. Our first two y values on either side of 2, it's going to be 3 plus 3. So if you want to put the 2 in front, you can. It's 2 times 3 plus 3, or 3 plus 3 times 2. It doesn't matter. Plus the next width of 3 times the sum of the values on either side. That's 3 plus 1. Plus the next width of 0.6 times the sum of the two values on either side. That's 1 plus 5. Plus the last width of 1.4 times the sum of those two y values on either side. 5 plus 8. Close that, close the brackets, okay? And you can do it like that too when you have equal subintervals. So you don't have to necessarily factor out the delta x. You can always do it like that. That works every time. So notice we're still using all the y values on the interior. We're still using them twice. They're still doubled, but each one of them is associated with a different width. So we can't just double them together, okay? So pretty fast, pretty easy when you have the data in front of you, but you are limited. All right, part B. Could any of these approximations represent approximations of areas? Well, all of our y values, again, are positive, right? Does that mean all the ones we don't see are positive? No. Were we given any kind of indication like we did up here that f is positive for all x's? No. So we'll just say here, not enough info. We don't know. Not enough info. We don't know if f is greater than or equal to 0 for all x in the interval from, where are we going, 1 to 8? We're not told that. We're not given the equation that we can analyze. We're not given a graph that we can look at, so we don't know. It might be, but it might not be. All right, and then part C, a review again, approximate f prime of 7. This is a review question, and this is the one that is most likely you'll see, f prime of 7. Notice 7 is not in the chart. It would fall right in there somewhere between 6.6 and 8. So in this case, it makes sense to use the 2 points on either side. So I'll go ahead and do that. So again, it's changing y, right minus left, so 8 minus 5, all over 8 minus 6.6. And there's your 2 for 1. Difference quotient, method is indicated. Those values are from the table, and it's numeric. All right, so there's example 11. Got it? Fun, 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 fun. Comments, questions, quips, quotes, concerns, good, clean jokes, anyone? No? Been a while since we've told jokes, right? We're so busy trying to catch up.
I know you have a dad joke, Corpy. Come on, share it with us.
I don't. I really don't.
Sad face.
Yeah. Let's see. Let's come back up here to area under the curve. So this is right after example 4. We have to interpret what the definite integral is, all right? Because the definite integral up to now has just been area, and unfortunately, it's not always area. The definite integral is not always area, okay? What it is always is it's the net accumulation over the interval, okay? So if you look at this diagram right here, imagine that you knew the magnitude of the 3 areas that are bounded above and below, okay? Let's say that we're looking at a guy, he's in Vegas and he's gambling, okay? And we're watching him, okay? Let's say the area of this first region from -5 to -2, let's just say that the area is $8, okay? Or it's $8. Let's say that the area then from -2 to 3, let's say that the area is 7, okay? Now those are negative y values down there, but if we found the area, we would have to change the sign of the integral because the integral is going to give you negative numbers, okay? And let's say that over here the area is 5. So if you know the areas, the positive value that represents the areas of these 3 regions, here's what the definite integral tells you. The definite integral always gives you net accumulation, which means it's a vector. So if you're going from left to right, which is the way we traditionally go, think of this as like chronological order. Okay, things are exactly as they seem. So if it's above, then it's going to amount to a gain of the magnitude of the area. But if it's below, we have negative y values. Area can't be negative, but the fact that the area is 7 and it's below, this is going to represent a loss, okay? A loose, I put 2 O's instead of 2 S's. And again, back over here, if it's above, it's another gain, all right? So we can figure out what this is. If I wanted to figure out the integral from -5 to 5 of f of x dx, first of all, again, remember we read this as from the bottom up. We say from -5 to 5. Is that left to right? Is that chronological? From -5 to 5? Yes. So look what we could say then. From -5 to -2, the area gives you 8. That means that the dude gained $8, right? The area from -2 to 3 is 7, but because it's negative y values, it represents a loss of $7. And then, of course, the positive on the other side represents another gain of 5. So if you compute that, you get 6, right? 6 is the net accumulation of this guy's winnings. So you could say for this 10-hour period, if you want, he came out $6 ahead. Now, it doesn't tell us how much he has. He could have been a millionaire to start with, or he could have just had $1 to start with, okay? If we add 6 to what he started with, we get his current amount. But right now, without that, we could tell that he came out $6 ahead. That's pretty good, I guess. I don't know. I don't gamble much. Now, if you wanted the area, let's say you went to Sherwin-Williams and you had to paint that. Now you're not going to subtract the 7, right? For the area, because area is always positive, you have to add them. 8 plus 7 is 15, plus 5 is 20. That would be 20 square units, okay? So the definite integral, when you set it up, doesn't always give you area. It's a vector. So from left to right, positive y values are a gain, negative y values are a loss. But here's the thing. Area and integrals are closely related. You can obviously use the areas of the regions to help you find the integral. You just have to give them the correct sign, plus or minus, based on whether they're above and below. But you can even use the integral to find the areas if you wanted. You just have to know where the graph is positive or negative. In other words, if I integrated from -2 to 3, I'm going to get -7. Well, if I take the absolute value of that, or just change the sign, I get the area, which is +7. One of them can help you find the other. Okay, you just have to know where the graph is above and where it's below. That's important. Now, let's say not only we were watching this guy, but let's say we were filming him. Ooh, with our cameras, right? Kind of creepy. If you went home and you played that video backwards, what would it look like? Would you see him gaining $5 there at the end? If you played the video in reverse, instead of someone handing him $5 and him taking it, when you play it in reverse, it looks like he's giving the person $5, right? They say if you play Jaws backwards, it's all about a benevolent shark that gives, prosthetics to amputees, right? That's one way to look at it. So everything when you go in reverse is backwards, right? So look at this. If we integrate from right to left, everything is backwards. Everything above now is negative. You see him giving back the $5, and now everything below is positive. Okay, that's important. So now let's put the areas in there. Let's say the area here was $8. Let's say that the area here is 7, and let's say here it's still 5. What would the integral now from 5 to -5 be? Okay, and again, it's important to look at your intervals of integration on your definite integral. We read this again as from to. So if we're going from 5 to -5, that's backwards, isn't it? So let's see. What kind of 5 is it going to be over here? Well, it's above, which is normally positive, but because we're going backwards, it's going to be a -5. And then the 7, which is below, which is normally negative because we're going backwards, it's going to be +7. And then again, the last piece here, 8, which is normally positive because we're going backwards, is negative. And you end up with -6, right? Which makes sense. If you watch it going forward, he comes out $6 ahead. If you watch that film going backwards, he's $6 behind. Okay, so it's super important. You can use areas of regions to help you find integrals. You just have to consider 2 things. Are we going from left to right or right to left? And are the y values above or below the x-axis? Okay, this leads us to a very, very important little property. The integral from a to b is the opposite of the integral from b to a. Okay, very important. So if you ever need to flip your interval of integration, you can do that so long as you change the sign out front. And you're going to see that might be useful because if we set up a problem and we have a negative here, that negative, we might forget to distribute it down the line. But if I can flip that and change that to a positive, now I have a positive out front, okay? So if you flip the interval of integration, that's fine. Just change the sign out front, all right? Now let's jump down here to example 7, okay? It's kind of an extension of what we just did. I took this graph off an old AP exam. It was a multiple choice question, and the question was just part E. So let's just do part E, okay? It said to evaluate this. Now let's look at what it says. It says the graph of y equals f is shown below. If a sub 1 and a sub 2 are positive numbers that represent the areas of the shaded region, then in terms of a sub 1 and a sub 2, evaluate this. Okay, well, it's 2 separate integrals, so let's focus on the first one. What is the integral from -4 to 4? From -4 all the way to 4. First of all, is it chronological? Is it left to right? Yes, so things are as they seem. So everything above is going to represent a gain, plus, and everything below represents a loss. So that first part there is going to be a sub 1, positive a sub 1, right? And then minus a sub 2, based on, very similar to what we just did, except we're doing it abstractly. A sub 1 minus a sub 2. You think that's going to end up being a positive or a negative number based upon the size of those areas? Probably negative, right? He's losing more. He's going to come out behind. All right. And then we have -2 times. I'm going to put a bracket here. What is the integral from -1 to 4? Well, -1 to 4. We're losing again, right? So if a sub 2 is the positive magnitude, What kind of a sub 2 are we going to put there? Positive or negative a sub 2? Negative, it's a loss. Good. So if we know the areas, the positive areas, we can evaluate integrals, but we're in charge of assigning the correct plus or minus sign. Now, if we simplify this, we get a sub 1 minus a sub 2. A negative times a negative is a positive. And now we can combine like terms. 2 of those minus 1 of those leaves 1 of those. And the answer is a sub 1 plus a sub 2. Okay. All right, real quickly on your own, do part C. Just do part C on your own. On your mark, set, go. I'll pause the video. What'd you get? A sub 2 or negative a sub 2? A sub 2. Good. And the reason is it's not negative, even though it's below, because we're going from 4 to negative 1, which is reverse chronological order. Okay? Reverse chronological order. Excellent. So you get that idea. That's awesome. Let's go ahead and look at this then. Example 8 is another extension of that. Oh, you didn't see me write it. Here we go. Example 8 is another extension of that. This is what we saw on, I think, a 2010 free response question. Let's just look at example. Let's just look at example B. Okay, we'll just look at example B. The graph of a function y equals f of x is composed of 3 line segments and a semicircle. Part B, evaluate the integral from -7 to 0. All right, so step 1, we're going from -7 all the way to 0. Is that chronological? Is that from left to right? Yes, that's the first thing you consider. So everything is as it seems. So if I can find the area of these regions geometrically, I can assign them a plus or minus sign, right? Well, because it's made up of line segments and circle segments, we can find the actual area using not Riemann sums, not trapezoids, but just geometry, right? This is a triangular triangle, so let's calculate it. 1/2 the base. The base is from -7 to -2. How far is that? That's 5 units, right? And then the height is just 1. So this area is 5/2 or 2.5. What you want to do is write the area of that region inside the region. And then when that number shows up in your calculations, you're indicating your method. This piece here is what fraction of a circle? It's 1/4 of it. So you take the area of a circle, which is pi r squared, and divide it by 4. What is the radius? It's 2, right? So 2 squared is 4 divided by 4. This area is pi. So now, what would be the integral from -7 to pi? Well, what type of 5/2 is it going to be? -5/2, right? Because we're going left to right and it's below. And then what type of pi is it? Positive pi. That's my favorite type of pie. Try to order a positive piece of pie in a restaurant. Okay, now the area, if we wanted to paint that, the area is positive pi/2 plus pi. Get it? Positive pi/2. But the net accumulation is pi/2 or pi minus 5 pi. Okay, let's do this one from 5 to 2. Now notice this happens every once in a while. This is 1, 2, 3, 4, 5. It crosses at a part that's unmarked. Can we figure out where it crosses? If you had to guess, what would you guess? 4.5? That's actually correct. All right. Now, what I had you do originally on part A is to write the equation of this line segment. Write the equation of the line segment, okay, in Taylor form, and set it equal to 0 to find the x-intercept. Okay, but it does come out to be 4.5. And since we're a little short on time, we'll just leave it like that. So let's go ahead and figure out the integral now from 5 to 2. Well, the integral from 5 to 2, okay, so let me draw a line down here at 5. So I need to find this area, and I need to find this area, right? Now, first of all, if I go from 5 to 2, is that forward or backwards? That's backwards. So that's where you might want to make a note to yourself. Everything is going to be opposite of what it seems. So let's just go ahead and calculate the areas of these triangles. This little fellow over here is 1/2 the base. The base is from 4.5 to 5. That's 1/2 of a unit. And then the height is 1. So that ends up being 1/4 or 0.25. Again, that's the area. The big fella over here, the area is 1/2 the base. The base is from 2 to 4.5, which is 2.5 units, right? You can leave it as 2.5, but 2.5 is the same as what as a fraction? 2.5 is 2 1/2, which is the same as 5/2, right? I just like to have everything as fractions. Okay, that's the base, and then the height is 3. So that ends up being 15/4. Remember, on a free response, you could just leave them as exact answers. Okay, but you do want to write the area inside the region. And now those two numbers, 15/4 and 1/4, they need to show up in your calculation. All right. So here we go. From right to left, what type of 1/4 is it going to be? Positive or negative? Positive, right? Normally it's going to be negative because it's below, but we're going backwards. And what type of 15/4? Negative. Okay, good. And there's really no reason to simplify that, but if you wanted to, you do get negative 14/4. Right? What would be the area of that region if you wanted to paint it? It would be 15/4 plus 1/4 would be 16/4 or 4, right? So remember, area is always positive. Area is always positive. You can use integrals to help you find areas. You just have to integrate over the regions where you know are positive, and then you don't have to do anything. And if you integrate over a negative region, you have to manually make it positive. That's how you can use the integral to get areas. But if you know the areas, you can evaluate the integrals. You just have to give them positive or negative signs based on whether they're above or below. All right? So far, so good? Now, I'll just throw this in here. If you're ever asked to find an area on a calculator question, then you don't have to worry about where the function is positive or negative. You could just take the integral from a to b, and you could take the absolute value of the function. That turns everything positive, and then you integrate straight across. But that's not the way we want to do it if we don't have the calculator, because that makes it really, really hard. Now, let's backtrack up here to example 5, okay? We've been practicing using areas to find integrals. I want to use the integrals now to find the areas, okay? So here's a piecewise function. If f is 3 to the left of -1, and the line 2 minus x at -1 and to the right, write and evaluate an integral expression that gives the area of the region bounded by the graph of f and the x-axis from -3 to 3. Okay, so it did say the word area, so now we're on positive alert, positive alert, positive alert. Let's go ahead and sketch the graph. Here's -1, and it's 1, 2, 3. There's 3, and it's going to be an open circle, and it's a horizontal line to the left. So something like that. And now we need to figure out where the line picks up at. So remember, what's the limit from the right? If you use direct substitution, 2 minus -1 is 3. So it actually plugs the hole, and now it has a slope of -1. So the y-intercept is 2, and that's enough to draw it like this. There we go, looks good. And now we can figure out the x-intercept here. The x-intercept is going to be 2. You can tell by setting that equal to 0. All right, so there's kind of what the graph looks like. It's continuous, but not differentiable, right? It's continuous for all real numbers, but it's not differentiable at -1. There's a sharp turn. All right, so now we're going from -3 to 3. So let's come over here. I'm going to draw a vertical line. We'll just call this -3. And then I'll draw another vertical line here, and we'll call this 3. So here's what I want to do. I want to find the area of this region, the area. Now it said to set up an integral. You might be asked to set up an integral. So let's do that. The area of the region then is going to equal, well, notice that it's going to be positive already from -3 to 2. So if I just integrate from left to right, it should be good. It's going to be the integral from -3 to 2 of f of x dx. That's going to give us a positive number. Would you agree? Because we're going from left to right, and my y values are positive. But if I just integrate from 2 to 3, what type of value is that going to be? It's going to be negative, right? Because I have negative y values. Okay, so just like if we were doing Riemann sums, you know, we use the y values. It's going to give us a negative number. Since I want to find the area, how can I make that negative quantity positive? Just put a what in front? A negative, right? If I put a negative in front of the integral, that'll take this quantity, which will be negative, and a negative times a negative is a positive. So that's one way to do it. Is there another way to do it based on what we already said? The first piece is good, negative 3 to 2 f of x dx. But was there another way to make that integral from 2 to 3 positive instead of negative?
From 3 to 2.
What if I went from 3 to 2? Now that's going to give me a positive number, right? Because I'm going from right to left and it's below, and now I can add them. And that kind of, again, reinforces that little property we had. If you flip the interval of integration, that's fine, just change the sign out front. So instead of subtracting from 2 to 3, let's add from 3 to 2. That's going to give you the area, okay? So again, you can use integrals to find areas. You just have to know where is it positive, where is it negative, and then you have to manually make it positive, okay? Now, can we actually find the area? Yeah, we don't have to use Riemann sums or anything to find the area because we have a trapezoid laying down and a little triangle, or if you partition it, we have a rectangle, a triangle, and another triangle. I'm not going to worry about doing that, okay? But there you go. That's setting up an integral to help you find area. Okay? All right. Let's look at this property. I know I'm jumping around here. It's kind of fun. It's kind of exciting. This is another property. We just saw if you flip the interval of integration, you can change the sign out front. This is the one that I call the travel agent property. It used to be before you could do everything online by yourself, you'd hire a travel agent who would kind of map out your, not only your entire vacation, but specifically your itinerary to get you from point A to point B. This one says the integral from A to B is the same as the integral from A to C plus the integral from C to B, okay? So it's real easy to understand if you have something like this is f of x, and you're trying to integrate from A to B, something like that. Let's say this is what you're trying to find. Well, ideally, let's do it in terms of like flying, because it's easy to do. Ideally, we would like a direct flight from A to B, right? That would be nice. We get there faster. We don't have all the, you know, the burden of the layover. But that's not always the case. Sometimes you have to have a connecting flight, a little bit of a layover. So if you want to go from A to B, you can actually choose a value C, which doesn't even have to be on the interior. It could be outside of it, okay? And now, all you have to do is integrate from A to C, and then integrate from C to B and do well with those results. Add them together, right? So the way we would read that then is the integral from A to C plus the integral from C to B. And those would have to line up on that diagonal. Because remember, C is where we end up at. That's where we have to then depart from on the next flight. So I think you can clearly see geometrically that if we add those two pieces together, we get the whole thing, right? All right. That's kind of important because if you notice over here, if I really wanted to use specific parts of the function instead of just generic f of x, I'd actually have to split it up and go from -3 to -1, and then go from -1 to 2. Why? Because the piecewise function was defined by different pieces there, okay? But I'm not going to do that. Okay, so that's called the travel agent property. Now, let's jump down here and do some travel agent type problems. Okay, example 12. Travel agent problems. I think I'm really going to go back to the summer and kind of redo the sequence of this section. I like the way I'm doing it now better. I know my handwriting is horrible. That's supposed to say travel agent. Travel agent problem. Okay, so you have some random information about a function that's just given to you. For instance, we know that the integral of some function f of x from 0 to 10 equals 17. Okay, 17 is not necessarily the area, but it's for sure the net accumulation. For the same function from 0 to 8, we know the net accumulation is 12. You're going to be asked to use that information to evaluate something else about that function. And in this case, it's from 8 to 10 of 3 times that function plus 2. Okay, so here's what you want to think about this. Think about this as flights. I can fly directly from 0 to 10, and that gives me a 17 value. But I can also fly from 10 to 0, can't I? These are two-way flights. So if the integral from 0 to 10 is 17, what do you think the integral from 10 to 0 is? Negative 17. Yeah, very good. Think of these as two-way flights. And I can fly directly from 0 to 8 and get 12, but then I can fly directly from 8 back to 0, and that's going to give me what? Negative 12. So again, if you flip the interval of integration, you just change the sign of the integral value. So think of these as two-way flights. Now, what I have to do first is I have to separate this, okay? So the properties of integrals allow us to do this. Watch. If you have the integral of multiple terms, the definite integral or the indefinite, you could break them up into their individual problems. That's how we can just integrate down the line, right? Antiderivative. And we can also pull constant multiples out front. This is a hugely important one. If you have a constant multiple, he's there in the beginning, he's there in the end. You can pull him out front. So here's what we're going to do. We need to get at this f of x. So I need to kind of get rid of the 3 and the 2. So step 1, let's just split it up. The integral from 8 to 10 of 3f of x dx, make sure you have that right bookend, and then plus the integral from 8 to 10 of 2 dx. So that's just giving them each their own integral, their own dx. Now in the first one, I have that 3. He's constant multiple. I'll pull him out front. So that's 3 times the integral from 8 to 10 of f of x dx plus the integral from 8 to 10 of 2 dx. All right, so what I was able to do is to separate it to get at that right there. Okay, now I want to be able to fly from 8 to 10. I want to evaluate the integral of f from 8 to 10. Was that given to me from 8 to 10 or 10 to 8? No. So here's where we have to play travel agent. We have to map our own itinerary. So here's what we're going to do. 3 beefy bracket. Okay. Now here's what we do. We have to start at 8 because that's what the lower bound is. We have to start at 8. What's our only option if we're at 8? We can only fly to where? 0, right? That's the only place we can go. So I have to fly to 0, f of x dx. Plus, now I'm at 0, okay? I would like to get to 10. Is there a flight that takes me from 0 to 10? Yes. Now, it may be that we don't. We might have to have 2 connecting flights, but in this case, there is one that goes from 0 to 10. So notice that's that additive interval property. I'm not going from 8 directly to 10. I'm going from 8 to 0 plus then 0 to 10. And then over here, we still have the same thing, 8 to 10 of 2 dx. Okay, so now we're ready to evaluate it. And I would recommend evaluate everything at one time. So here we go. 3 parentheses or brackets. What is the integral from 8 to 0? Well, if 0 to 8 is 12, then 8 to 0 must be negative 12. Yeah, so you don't even have to rewrite what we did up here. If it helps you to see that, that's fine. Just know that if you flip it, you just change the sign. And what is the integral from 0 to 10? Is that given? That's 17. Okay, so that's good. Now, how do we evaluate the integral of 2? Well, this is pretty easy. If you're ever integrating a definite integral of a constant, think about what the constant looks like. The constant is a horizontal line. In this case, at 2, right? That's y equals 2, which graphs as a horizontal line. And we're integrating from 8 to 10. That's from left to right. So that's just the what of this region here. It's the area, right? And that's a rectangle. Or in this case, it's a square. 10 minus 8 is 2, so that's the width. The height is 2. 2 times 2 is 4. Yeah. So you can always draw a horizontal line, find the width, multiply by that value. And on a free response, we're done, yes? That's a numeric answer. These make great multiple choice questions, though, so let's go ahead and keep going. 17 minus 12 is 5. 5 times 3 is 15. 15 plus 4 is 19. And that's your answer. Travel agent problem. It's so much fun. Okay, you want to try one on your own? I think you do. Try example 13 on your own, okay? On your mark, it said, I'm going to pause the recorder, go. All right, so real quickly, example 13, we have f of x and we're given some intervals, okay? The key is to start with this and work backwards. Now, f of x divided by 2, that's the same as 1/2 times f of x. So I'm going to pull the 1/2 out front immediately and say it's -6 to 3 of f of x dx. And then minus the integral from -6 to 3 of 3 dx. Now, just a little word about AP culture. If you forget this last dx on the right side, you're probably not going to lose a point because it doesn't affect the answer and they let it slide. Not that it's correct, they let it slide. But if you miss the dx on the interior, oof, now that's huge because now you're not shutting off your integrand and you're saying that your integrand now contains an integral, all right? So it's very important to make sure you have both bookends. Now that I've separated it, I need to use what I'm given. So let's see, this is the itinerary part. I need to start at -6, okay? I would like to fly to 3. Can I fly to 3 from -6? No, the only place I can fly to is where? 4. Now notice, I'm not going to spend the time writing those flip. I know that I can flip those and just change the sign. So I guess I can only fly to 4. All right, so make sure we put f of x dx. Let me scoot this over. It'll take a while. All right. Plus, now I'm at 4. I'm at 4, right? You have to start at the same place the plane dropped you off at. Now, I'd like to fly straight to 3. Can I fly straight to 3 from 4? No, but I can fly to 7. See that? F of x dx. Okay, plus, now I'm at 7. I'd like to fly to 3. Can I fly to 3 from 7? Yes, okay, so I had to have 2 connecting flights. Wow. F of x dx. Now, if you want, instead of writing the integral on this last one, since you did split it up, you can evaluate that. Here's 3, right? And you're going from -6 to 3. So that's 9 units here and 3 units there. What's 9 times 3? 27. So you could call that 27 if you want. And now we can plug in, okay? So here's where we plug in. If we have to flip the interval of integration, we just change the value. So what is the integral from -6 to 4? Well, if 4 to -6 is -3, then -6 to 4 must be +3. Yeah. And what is it from 4 to 7? Well, that one was given. That's 5. We don't have to flip that one. What is it from 7 to 3? Well, if 3 to 7 is +9, 7 to 3 must be -9. And there's our answer right there. That's your free response stopping place. If you want to add that together, you can. I'm not going to, okay? Everyone good with that? Travel agent problems. Kind of fun, kind of. All right. There are 5 questions on AP Classroom tonight. I have one last thing to tell you about. There are 5 questions due Monday, but they only deal with the numeric methods, not the travel agent problem, okay? The last thing that I threw into this section was this little theorem up here. If a function is continuous, then it's integrable, okay? We had the sister theorem earlier in the year. Differentiability implies continuity. Remember that? If a function is differentiable, the arrow means implies, then it's continuity, or then it's continuous. The contrapositive is also true. Oops. If it ain't continuous, then it ain't differentiable. Okay, that's what that means. Well, here's the new one. If a function is continuous, then it's integrable. That just means we can find the area under the curve. And if it's not integrable, then it's not continuous. Now, if you want, you can use the transitive property. If it's differentiable, then it's continuous, and therefore it's also integrable, okay, if you want. Now, notice what this theorem does not say. It doesn't say that if it's not continuous, it's not integrable. In fact, you can integrate functions that have discontinuities in them. As long as they're holes or jumps, it's never going to be a problem. Asymptotes may or may not be. Let's revisit Senor Salta, okay? The absolute value of x over x. Remember him? Senor Salta. Hola, Senor Salta. Hola, Coach Richter. También. So you saw that, remember? Here's 1. It graphs as a horizontal line 1 everywhere to the right of 1. And it jumps at 0 from -1 to 1. So it's the one time really where 0 over 0 does not mean whole and limit still exists. It means jump. We're trying to integrate from -2 to 3. Okay? Now, even though the function's not defined there and there's an open circle, if we can find the areas of these two regions, we can assign them our own sign and give them the integral value, okay? And it turns out that having those open circles does not mean that you have an infinite area, you know? You might think that because it's open there, there's like a little hole, now the area can leak out, right? And that would be infinite area, but that's not what happens, okay? Holes and jumps, that doesn't happen. So what would be the area of this little piece down here? Well, it's 2 units wide by 1 unit tall. It has an area of 2. An area, we put the area in there. This one is 3 units wide by 1 unit tall. The area is 3. So if we wanted to paint the region, we would have to order enough to cover 5 square units, right? And maybe an extra coat or 2 where the holes is so that the paint clogs the hole, you know, in practicality. But the area is 5. But what is the integral from -2 to 3? Let's show our work. Well, what kind of 2 is it going to be from -2 to 0? Should be -2, right? Because we're going from left to right and it's below. So we assign it a negative value. It's a loss. And then what type of 3 is it from 0 to 3? Positive, right? So the net accumulation is what? 1. That makes sense, right? We lost 2 and then we gained 3, but we still netted 1. So here's an example of a function that's not continuous, yet it's still integrable. We can find the area of the curve. Just for kicks and giggles, what would the integral from 3 to -2 be? -1, right? Yeah, got it? Okay, we're done. There's 5 questions. They just deal with left endpoint, right endpoint, midpoint, trapezoidal, not the travel agent problem, okay? Starting on Monday, well, I don't know. I'll let you know on Tuesday when you get here how we're going to do it. I've come up with this idea to like review and learn new stuff simultaneously at the same time. Okay? Just do one with our right eye and our right hand, and then the other with our left eye and our left hand. We'll be multitasking. Okay? New stuff with the right side, review with the left side at the same time. Okay? I have to speak out of both sides of my mouth at the same time. I got to practice that this weekend. Any comments or questions? Yes.
Good luck with that.
Thank you. All right, y'all can log off now. Thanks, Haley, Hunter. Thanks, Landon. We'll see y'all later.